Yes, so this is A Brooksbank, and he's going to be talking to us about tensors.
And Nate's like, thank you, James, for putting me on the spot there. It's not just me, actually. It's me and my lucky Lego character that James just gave to me. Oh, thank you, James. I'll just put him up here, shall I? There we go. Great. So it's lecture 2. I'm going to continue more or less where we left off yesterday, talking about linear methods for tensors. Let me just say to begin with, I sent Chris some stuff yesterday, but I haven't quite managed to send it to you today. But I'll just mention that I do have some lecture notes for this lecture as well that I can send after the lecture with a bit more detail than I'll go into today. Right? I'll probably skip a few broad strokes, and if you want to look at the detail in particular, those notes will contain some references to other places in the literature where you can learn more about these things. I will do a brief magma demo again today, but it won't be as much, so I'm going to leave the projector screen up for now and kind of write on all of the boards, and then that will just rely on my technological acumen to bring the board back down again at the appropriate time, so we'll see how that goes. Great, yeah, so let me just remind you about where we were yesterday. So really, if you remember, the point of my lectures is to sort of introduce some linear techniques, right? So linear invariants of tensors that you can solve by systems of linear equations is what I mean, right? And the idea is that these linear invariants also have algebraic structures of their own that hopefully we can leverage to shed some light on the structure of the tensor. Right? So broadly speaking, that's what these methods allow you to do. So they're efficient because they're just solving systems of linear equations. And so in the background of the talks is always an eye towards computation as well, right? You know, so hence the magma demos, but I'll mention computational issues as they come up. So last time we spoke about the centroid of a tensor. We've since seen Josh's talk this morning, where he talked about the centroid in a bit more detail, in a bit more generality, right, for n tensors. I'm going to go back to bimap notation again today. So let me just remind you what notation we were using last time. Let's see. So let's let U cross V W be bimap. Yeah, and I'm going to largely stay away from the original sin, as Christopher may have put it, of choosing bases today. So I'm going to say mostly basis-free. But let me just remind you that when we do pick bases, I'm going to take that sort of front-to-back approach, right? So I'm thinking of the tensor as being sliced from the front to the back. And we've seen various people talk about this in various ways, so hopefully by now it's a fairly natural idea to think about taking something like this, choosing bases for U, V, and W, and then producing what I was calling a system of forms, right? So you'd have like M1 up to ME, let's say, where E is the dimension of W, and the dimensions of the MIs are going to be C by D, where C is the dimension of U, and D is the dimension of V. Okay, so this probably won't play much of a role until we come to the software demo later, but just to kind of remind you what it is that the software is telling you when we get there. Great. So, yeah, so let me just remind you what the definition of the centroid is then. So the centroid of the bilinear map, denoted sen star, consists of all triples of endos, really, satisfying And I'm going to separate these conditions actually for today. So let me begin with one of the conditions. U x star v is the same thing as U star v z. So remember by endos what I mean are triples x, y, z, where x is an endomorphism of U, y is an endomorphism of v, z is an endomorphism of w. So this is the first condition. And the second one is that U star vy, same thing on the right, U star v z, and finally U x star y equals U star vy. And we want these conditions to hold for all U and for all v. Okay. Now, of course, there is some redundancy here. I recognize that you don't need all three of these equations. But I want to separate them in this way for a reason that I'll come back to a little later. Right, so...
Pete, the very bottom one, I'm not sure I follow what you're trying to do there. Should the first y be a v or something?
Oh, yes, quite.
But
Will we help you now? Yeah, thank you. Right. Great. Yeah, so what we learned, I guess, last time was that if you have a set of endomorphisms that satisfy all of these constraints, then you get certainly a linear subspace, of course, right? But in addition to that, we discovered that this structure is a ring, first of all, and it's a commutative ring, second of all, right? And I left you with an exercise. In fact, I think several of us at this stage have left you with the same exercise, which is to confirm that this is a commutative ring, right? I'll come back to this a little bit later, but if anyone's played around with it and sort of sees the trick for proving the commutativity aspect of this, then something that comes up a bit later will perhaps make a little sense. Right, so we've got these three conditions that make up the centroid. And so the question I'm going to begin with today is, suppose we just took, not all three of these conditions as I've separated them. What if we just took, one of them, for example, right? The question is, do we gain any additional insight into the bimap by just considering one of these conditions, right? And indeed, well, you can see that if we just take one of these conditions, we're still going to be able to find all of the things that satisfy that equation efficiently, right, by solving a system of linear equations. But a question you might ask is, does the set of all such things have a nice structure similar to the centroid that we can exploit, right? And if you remember, we didn't really go into too much about how the structure of the centroid kind of informed what we talked about last time. But we did see that if the centroid, for example, was a field extension of the original field, then we could rewrite the entire tensor over that field extension and thereby sort of condense our data a little bit, right? So that's sort of one utility of the centroid. Another one, if you remember, was that we could sometimes kind of block diagonalize our data by using the centroid. And in the demo that I gave, I was sort of a little bit light on detail about how you actually go about doing this in general. But you can believe me that you take the structure of this commutative ring, you kind of understand its structure algebraically, and that structure then translates back into decomposing the different modules of the underlying tensor, and then you can so that leads to a kind of a block decomposition of the tensor. And so what we want to do now is to kind of do the same kind of thing, but just by focusing on one of these things. And the one that I'm going to focus on is this one, which I'll call middle scalars. So this is a condition that just allows you to kind of pass scalars back and forth between these internal components. I'll call this condition here, let's say, left scalars. And I'll call this condition right scalars. And just to connect this to Josh's talk a little bit earlier, if you I'll maybe tax your memory a little bit, but if you remember, Josh introduced some polynomials, right? Some linear polynomials. and looked at the ideals generated by those linear polynomials and associated those to these different objects. And this one here, I guess, corresponds to what Josh was calling x0 minus x2, I think. Well, it's probably x1 actually in the labeling, isn't it? This one was x0 minus x2, and this one would be x1 minus x2. So I'm sure you've got all of Josh's talk kind of stored in your brains, but just to sort of connect it to the language that he was using a little bit earlier. These are individual sets of solutions that correspond to these polynomials. So I'm going to focus on this one, the middle scalar one. Why, you may wonder? Well, I don't know. I just am. But I will give you some justification. So let me just begin with a bit of motivation here, which it will surprise you not one whit to learn is coming from isomorphism, right? So we'll just start with the group, with a tensor isomorphism problem for three tensors. And you've seen various forms of this problem at this stage, right? And recently in Yu Ming's talk, he spoke about different varieties of tensor isomorphism problem. I'm going to go with the most generic one for the time being for bimaps. So motivation. Three tensor isomorphism. So let me begin then by taking this bimap U cross B to W. And I'm focusing on this condition here, the fact that we can pass scalars back and forth across this star here, right? These are all F vector spaces, I'll just assume that, right? So we've got some ambient field that we're given as part of the data here. And so what I can do is I can form the tensor product over the field that I'm given, U tensor V. And just as a concrete way to think about this as just F to the C cross D. So it's just C by D matrices, space of C by D matrices. And then I want to think about a particular bimap here that I'll call a tensor bimap. And the way to think about the image of this is that something like U comma V. So thinking about these as row vectors, you can think about this as just, if this is a row vector, this is a row vector, think about this as U transpose V. Okay, so that's what the map does to take you from here to here. Okay. So the nice thing about this map is that it's a universal map. So what that means is that there's a unique linear transformation between this F vector space and this F vector space. Right? So there's a unique, I'll call it tau, let's say, that takes you from here to here. Okay. Great. So far, so good. Tensor isomorphism then. So if we're going to talk about the tensor isomorphism problem, I better bring another bimap into the picture here. So let me think about this as being actually just bimap 1. I'll call this one linear transformation 1.
Can I interrupt to ask a question, because I'm kind of confused about whether your vectors are rows or columns. Over here, I thought you had row vectors.
I do have row vectors, yeah.
But then here you're doing the transpose?
Well, this is right, isn't it? Yeah. This is going to be a C by D matrix.
I think it's going to be a 1 by 1 matrix.
I don't think so.
If U is a row vector, now you've turned it into a column. Okay, you're right. I don't know. Something here. I'm learning today. Sorry. Okay. Sorry.
No, that's good because it
Yeah.
helps us all kind of like into
Yeah.
the. It's going to be a rank 1 tensor that comes out of this.
It's brilliantly correct.
Thank you. Yeah. So I'll get rid of the units now, but I'm going to put another tau 2 here that goes along with the star 2. So I've got these two bimaps, and they have their own maps from this tensor product to W, right? So basically what I'm doing at the moment is I'm digging a little bit deeper into, if you cast your minds back to Josh's talk yesterday, he spoke about brute force, right? If everything in sight is finite, and let's just for the sake of argument assume that our field is finite here, right? Because that sort of is a context that is sort of more familiar, more interesting to me, I guess. Thinking about the complexity issue rather than decidabilities. So even in the finite field case, what Josh said was, this kind of boils down to just a simple search, right? You just kind of search through all invertible triples of matrices and ask the question, does one get mapped onto the other one? And we talked a little bit at the end of Josh's talk, if you remember, about variations of that and what does that mean. Taku, you were sort of asking some questions about how do you actually do this in practice. So this is actually a situation that does come up in practice, right? You're often confronted with this situation. So let's kind of drill down a little bit into what you would do from this point. Okay. So we've got these two maps. What we can say is the following: that if well, let's just say if star 1 is isomorphic to star 2, then if you think about the kernels of these maps are going to be living inside this space, right? So the kernel of tau 1 and kernel of tau 2, then we can say that the kernel, these two kernels, the kernel of tau 2, tau 1, and the kernel of tau 2, they're not necessarily equal, but we do have this action of the group GLU cross GLV on this space, right? It's kind of a natural action which is kind of acting, GLU is acting here, GLV is acting here. And what we really want is for these two kernels, which are just subspaces of this thing, to be in the same orbit, right? So these things must be in the same orbit. Must be in the same GLU cross GLV orbit. Okay. So task number 1, if you're given this situation, would be to try to decide that question. You can compute these maps very easily. Given a tensor, you can calculate these tau 1 and tau 2. You can compute the kernels just using null spaces. All very good. And now you're confronted with this question of basically having two subspaces in some vector space and a group acting on that vector space. And you're asking the question, is there a group element that transports one subspace to the other? Right? And Taku, this was if you remember the question that we were talking about at the end, right? This subspace transporter problem, as it's called. So let me just actually write it down. So subspace transporter problem. So given a group G, acting on an F space B, let me just change that to X so we don't get confused, and Y1, Y2 subspaces of B. Find G and G with Y1G equals Y2. Okay. That's sort of the general formulation of this problem. We're going to try and apply it to this particular situation where you've got the general linear groups, the direct product of two general linear groups acting on a particular space, the tensor product. But there's nothing particular about this action that's all that useful, it turns out, right? So if you think about what these kernels could be, they could literally be anything. And so there's nothing particular about the structure that we have in place that's going to help us solve this problem, right? So what one is resorted to in this situation is to simply list the orbit, right? So you take your subspace kernel of tau 1, and this is where the brute force comes in, right? Now you start kind of computing translates of this subspace, and you stop if you find one that's equal to the other one, okay? Now you can obviously see the problem with this. We talked a little bit about it last time in Josh's talk, that the problem is that GLU cross GLV is an enormous group. U and V don't need to be all that big before it becomes completely out of control, right? So there's no way you're going to list this thing. These orbits are often regular in the sense that there's no kernel to the action, right? It's going to give you like an orbit that's roughly the size of the group, basically, right? And so the motivation, coming back to why are we talking about this condition over here? The motivation is the following, right? So the problem here is that the space that we're acting on here is too big, right? So this tensor space is dimension c times d. The group that's acting is huge. It's like q to the c squared times q to the d squared. Q is the size of the field. So the question is there anything we can do, is there any way we can use sort of intrinsic properties of star 1 and star 2 that will help us to reduce this space, right? So that we're now not dealing with, this horrible orbit problem, maybe it's just a smaller orbit problem, right? Better yet, ideally, we can get enough control over the action on this on the resulting space that we can solve it not just by brute force, right? We could actually, apply some more intelligent techniques to try to solve the problem. So this is motivation. I'm not going to say any more about this problem. I just want to give you a feel for, why we're going to focus on the particular condition that we are right now. So how do we make this space smaller? Well, you tensor over something bigger, right? Is basically the point, right? So what would that be? Okay, so let's make a definition then. So let's let omega be a subset of mu cross mg. And let's say first of all, I guess I'm going to define this. So let's define U tensor omega V to be U tensor V, and then I'm just going to mod out by a bunch of relations, so Ux tensor V minus U tensor Vy, where, well, you know all the quantifiers, right? So the xy's are in omega, and quantifying overall u's and v's as well, right? So if I'm running through a basis, let's say u and basis v. So mod out by that thing, we call this resulting space the tensor over omega, and if omega's got any substance to it, then this space is going to be a much smaller dimensional space than U tensor V. Right? So the idea. So let's now say that star is an omega middle linear map. Let me just draw a picture that kind of explains this. So before we had this picture where U cross V goes in the star to W, before we factored down to the regular tensor product, we're now going to factor down to this tensor product. And we still want this unique map tau, let's say, that takes us here, right? So I can sort of, basically the language that we'll use is that the bimap star factors through this tensor product. Right? You still got this tensor bimap here. And now we're just working with quotients instead. So if this happens, we'll say that star is a middle linear bimap. And so the question arises now then, is there some natural set of scalars, if you will, omega, which is natural to kind of factor through, right? What's the best thing given a particular star to factor through? Or if you like, what are the bespoke middle scalars for that particular given bimap? Okay. And if you remember, I'm not expecting you to remember, but we asked the same sort of question with the centroid, right? What's the best set of scalars to think of it being an omega bimap in general? And so you just take all of the things that satisfy the relevant condition, right? So that's going to be our definition of the adjoint. So definition. Adj star is equal to the xy's. I'll just write E. Remember, I was using the letter E yesterday to be NU cross NV cross NW. Now, it's just the first two, but I still don't want to write it out, so I'm going to call it E, such that U x star V equals U star V y. Again, quantified overall u's and v's here. Okay. So we've got this set. It's a subset of endomorphisms. We again might ask the question, what's in this set? First of all, we'll notice that the 0 is in that. The identity is in there. So that's kind of two things that are in there. It's the solution of a system of equations, so it's a linear subspace. That means it has a linear subspace of dimension at least 1. Okay. That's going to be true of any pi map, right? When you compute this adjoints, you're always going to get a one-dimensional F space, at least a one-dimensional F space. So the question we asked yesterday is what use is this thing, right? It's useful because it comes equipped with some algebraic structure, right? What algebraic structure? Well, it turns out that this is a ring as well, but it's not necessarily a commutative ring. And it's also, for the sharp-eyed here, not quite a ring yet. Josh alluded to this in his talk earlier. There are some minor adjustments that we have to do. Like that. So in order to make this all work out, in order for it to be a ring, you need to have the opposite action in the second component. Okay? But if you do, this all turns out to be a nice associative ring. All right, let me just pause for a second, make sure everyone's on board, still awake. Great. Let's see where we are then. Yeah, so maybe I'll just quickly remind you then. I said I wasn't going to say very much about coordinates, but if we wanted to actually encode this adjoint as a linear condition, I'll just maybe write it here. It looks something like this, right? You're looking at the solution of all things that satisfy this condition. Transpose 4y, 4y. Okay. And now I'm going to challenge my technical abilities and try to give us a quick demo. Let's see. So sleep. Whoa, look at that. I'm actually impressed with myself.
We are impressed with you too.
Oh, thank you, James.
Why do we invite you?
So you may remember I was making a reference to a British baking show in the last talk, and I'll reference it again. This is one that I prepared earlier. So let me just copy and paste this thing over, and we'll have a look at it. Oh, I suppose I should start Magma first, shouldn't I? Oh, no, it was started. What was going on? Let's try again. Okay, so let's have a look at what we're looking at here. So we've got, again, a seemingly random collection of numbers. Let me just display what S looks like here. So these 2x3 matrices. I went away from my favorite field of order 8191, you'll notice, to a field of size 541. But again, these two matrices appear as though they've just got kind of random junk in them. And again, it won't surprise you to learn that they're not exactly random junk. They've just been disguised to look like they're random junk. Right? So our job is to kind of figure out, using the adjoints, what's actually going on here. Right? Great. Okay. So what do we want to know then? Well, maybe you just try this one first of all. Let me just try doing the centroid of this thing. And I'll just do dimension. Centroid of T. And we see that it's one-dimensional, right? So we're not learning anything about this tensor from the centroid. It's just a copy of the field. But now let's actually calculate the adjoint.
Hey, where does it say 1?
Oh, it does say 1, trust me.
Pete, you might be able to move the window slightly on your Mac.
Oh, I can?
You might be able to just drag it to the right.
Oh, yeah, that's a sensible idea, Josh. Yeah, I did tell you I was a technical genius, didn't I? There we go, that works. Yeah, so it's one-dimensional, so you don't have to just take my word for it. You can take Magma's word for it instead. So, yeah, what do I want to do here? What's your command, Josh? There it is, nucleus 1, 2. Is that right? So Josh, you didn't really use this word earlier, but I think you just went straight to adjoints, right? But this word nucleus sort of is a more general function that kind of gives you things like this as well, like left scalars, right scalars, and if you're dealing with tensors that are higher valence, they'll give you lots of other things as well, right? So it's a really useful general function. I'm using it today just to produce this adjoint. So let's now actually calculate the dimension of this thing. And there we see there is some substance here, right? So I said before that the adjoint is always going to be at least one-dimensional. What we're seeing here, in fact, is that it's not just one-dimensional, it's three-dimensional. Okay. So far, so good. So now what we need to figure out then is, well, okay, how do we actually use this information, right? What this is telling us is that there are some hidden symmetries in this tensor that we're not actually seeing, right? They're sort of encoded in this adjoint ring, but we don't know how to extract them, right? We don't know yet how to use the adjoint to kind of drag these things out. So what we need, and I'll just check on the time. Did I start at 3:30? Is that right?
So.
Yeah, okay. Good. So what we need then is a little refresher stroke mini course on the structure of algebras. Okay. Now, I'm going to say a lot of things. I'm not going to justify a lot of things. Let me just say that what I'm about to tell you is a classical theory that you can read about in abstract algebra textbooks of various kinds. For example, I think Hungerford is a popular one, right? You probably find some account in Hungerford, but you can also find things in Jacobson as well, right? So this is a theory that was developed by Jacobson, Wedderburn, who am I missing? Artin. You know, there's a number of people involved in the development of this theory of matrix algebras. So I'll just write a few things down. Really what I'd like to get to is like, how are we going to use this stuff, right? So I'll sort of tell you the structure, but how are we going to leverage that to kind of tell us something interesting that we didn't know about this particular tensor. Okay. Oh, right, so you can use this message. I've never actually taught in Germany before, so forgive me if I completely messed this up.
I think this is done so that you can tell that you haven't used it.
Yeah. My technique is atrocious.
You can use a regular eraser.
I could, yeah, but you know, I've just been watching everybody else use them. I just want to get in on the fun a little bit.
That's good.
Let's try this one. Oh dear. Hey, look, it's getting the job done, isn't it? Am I supposed to do this?
Wait, is this like a German thing? Do the boards like this?
It is a common thing in the German schools I've been in.
You never get hired in Germany if you do what I just did.
Is it everywhere in Germany or just some places?
No chance anywhere.
Well, that's a separate point.
Right.
Great, okay. So, next part of the lecture then, the structure of matrix algebras. So I'll just begin then with R, which is some subring of NV. I'm not going to worry about the NU cross NV cross NW, whatever. We'll just take any matrix ring. And let's define this thing. So you take all of the maximal left ideals of the ring and intersect them, you get something called a Jacobson radical. What else? So this is an ideal. And it's a nilpotent ideal. Meaning that you can raise it to various powers and kill it eventually, right? So,
Does left ideal mean that R acts on the left or R acts on the right?
I was thinking of R acting on the left, yeah. So R times I is contained in I. Yeah. But of course, there's also the intersection of all maximal right ideals as well. So, great. So that's our Jacobson radical then. So we'll say that R is so if J bar happens to be 0, we say that R is semi-simple. Okay. So so it should be clear anyways. So you can compute this thing. It's going to be certainly a linear subspace of R. It turns out to be an ideal. But in particular, as a linear subspace, it's got lots of complements, right? You can find complements to the linear subspace in R. But it turns out that you can also find complements that are themselves subrings, right? And these are what we've come to call, I guess, whether rightly or wrongly, Wedderburn complements, right? This is sort of after the Wedderburn from the Artin-Wedderburn theorem. So let me just state that fact. Oh, I get to have another go now. Let's see if I can do better this time. Maybe this will be the last time. Is that better? Nobody's commenting?
It's the erasure that they're waiting for.
It's a good group, that, James. That's showing my age, by the way. Anybody get that reference? No.
Right now, everyone has their camera out filming this video.
Look at this idiot. Is that good? Shouldn't subject myself to this, really, should I? This ridicule. Gives you time to think about nilpotent ideals. Okay, so right. So the fact then. There exist subrings S of R such that R is equal to J of R. So it says S and J of S is 0. So you can basically split up your matrix ring into a radical part and then a semi-simple part. Great, okay, so yeah, I'll refer to this thing as a Wedderburn decomposition. Okay, so far so good, but there's more, right? So we also know from this theory that S itself decomposes, right? So it's semi-simple. What that means is we can find ideals, minimal ideals inside S, and write S as the sum of those minimal ideals. So there exist well, let me just say minimal ideals. I1 through IN of R, S, sorry. Such that S is I1 so you can sort of decompose the semi-simple subring S into minimal ideals. And that's good too, right? But we're not done yet. So we also have some control over what these things are, in fact, these ideals. Right? So the last part of this is that each I sub j is equal to end d of, let's say, m where D is a division ring. And in fact, thinking about the context that we're in, where the field is finite, we can actually say that this D is going to be a field extension of the given field. So you can really think about this as, let's say, K to the M cross M. So M by M matrices, the ring of M by M matrices over a field extension. So K, that is finite. In the finite case. Okay. So that's basically the structure in a nutshell of matrix algebra. So first of all, decompose into radical and semi-simple parts, and then you can decompose the semi-simple part into the sum of ideals. And each one of those minimal ideals is itself isomorphic as a ring to the full ring of matrices over some division ring, or when you're in a finite case, over some extension field. Okay. So that's the theory. So that theory was developed 1930s, 40s. The algorithmic theory of this is also interesting to us, right? Because one of our objectives here is to actually utilize this theory to say something, computationally interesting as well. Actually, I think Yuming referred to some of this theory in his talk, but let me just mention a couple of names here. Ronyai, Ivanios. So throughout the 1990s, and there are others, by the way, sorry, I'm just naming a couple. So throughout the 90s, algorithms that will essentially discover this kind of decomposition given an associative ring, given a matrix algebra, actually compute these decompositions, the Jacobson radical decomposition into minimal ideals. So this is efficient in theory, it's efficient in practice as well. Practical implementations of this were largely conducted by James and myself, actually, with a little bit of help from Eamon as well, using METAX sort of tools as well. From if you're familiar with the METAX algorithm for decomposing modules, the practical version of this kind of utilizes some of those tools. So the point of all of this is that you can actually calculate these things. And what I'd like to do in the little bit of time remaining is to go back to our little toy example and see if we can reveal the mystery behind this seemingly random collection of numbers that we were looking at. So let's see if this still works. Ah, it does. Right. Great. So, so I promised you that James and I had actually implemented this stuff. So now we're going to press the button on the computer that tells us whether we're successful or not. So let's see, how do I want to do this? Yeah, okay. So J, comma, W becomes equal to, true to its billing, the Wedderburn decomposition of this ring edge. Okay. So here's J. And you can see that J is a matrix algebra of degree 5 with one generator. We'll just check its dimension as an algebra, as an ideal dimension of J is just for 1. So we've got this one-dimensional radical, and probably shouldn't surprise you then that the dimension of W should be 2, but let's just check. And there we go. So we have a one-dimensional radical, two-dimensional semi-simple complement, and that's great. What we can also do is calculate the minimal ideals of this thing as well. So let's do that. I'll just copy and paste this. So there's two ideals, and yeah, I'm not going to do anything else that's all that informative, to be honest. But let me talk a little bit about what you would expect these ideals to kind of look like, right? Yeah, so well, actually, we can just kind of look at one of the generators, I suppose, can't we? Let's do I1 becomes equal to ideals 1. So you can see that, yeah, it's organized into that kind of block fashion again, the U and the V But notice on the V here, there's nothing particularly illuminating about this mess of data that we've got here, right? And this is because we're in the wrong basis, right? We've got these ideals that are given to us, in the basis that we started with. What we would like to do, ideally, no pun intended, actually, is to kind of rewrite I1 in a nice way, right? So what we could do is, for example, if you think about what I1 must actually look like and what I2 must actually look like in a nice basis.
Can't really see that.
So it should look something like this, I claim. No, so star here, maybe 0, star, star, 0. And then maybe the other one, this is I1. The stars are all the same, by the way, it's not three-dimensional. And the other one would probably look like 0, star, 0, 0, star, something like that. So if we write it in a nice basis, these ideals should come out looking like this, right? How do we find that nice basis? Well, what we could do, for example, is take this single matrix here. We could compute its null space. We could do the same thing with this one, compute its null space, and then we can sort of cobble together sort of a nice basis consisting of null spaces, organized so that you're respecting the U and the V decomposition as well. Okay. And if you do this correctly, you'll end up with the ideals looking kind of like this. Okay. Now, I'm not going to do that. I'm not going to subject you to that. There probably are functions in Magma that we could probably harvest to do this, but I did what I did earlier, which is to prepare a dish for you. So let's go down and just copy and paste this matrix in, and you have to, well actually if you're interested, I will provide this code. What I did was basically commented out in green here, right? So you can sort of check all of that. But the resulting matrices are these things that come out of the whole business. So let me put those things in. What's going on here? Oh, there we go. So these x's and y's are not going to look particularly special either. These are the transition matrices, basically, that are going to organize the data back into this form, right? So if I was to rewrite I1 and I2 relative to this change of basis, they should look like this. Okay. But instead, let me do something slightly different, which is to apply the same exact change of basis to the original tensor. Okay. So we had our, where are we? We had our original collection of matrices that were in this list S. So what I can do is to just apply x on the left and the transpose of y on the right to this list. And if things worked out well, we get something that looks a lot nicer than before. Well, you might argue it doesn't look that nice, but notice that there are some strategic zeros here, or zeros in strategic places, right? So imagine again that this is a system of forms, so imagine these things are kind of stacked one behind the other. This one at the front, this one at the back. So you've got this 2 by 3 by 2 tensor. And what you'll see is that there's kind of zeros kind of running through from front to back, all right? So what we end up getting is one of those kind of step decompositions that I was showing you a picture of last time. And perhaps just to emphasize the point, let me just go back and recover that thing, possibly. Where are the images? Diagonal blocks, there we go. Oh, that's diagonal, sorry, face blocks, there we go. So this is the image that I flashed up at the beginning of the last lecture that exhibits this kind of behavior, right? So this would be kind of blocked up from this face that you're looking at right here. And over here is just this little toy example that illustrates how you can use this adjoint algebra to do the same thing, right? So the way that these images were created was basically using properties of the adjoint algebra. And I promised Martin I wouldn't do this, but I'll just say he may or may not talk about this next week at Pingree. Okay? I say may or may not because who knows what Martin will talk about. Yeah, so that's great. Let's see, do I have anything else to say, or can I give you a little reprieve here? Well, maybe I'll just talk a little bit about the plan for tomorrow.
Can I ask a question?
Yes, please. Yep.
With both of these methods to diagonalize, how sensitive are they to perturbations?
Yeah, that's a great question. And I'm definitely going to leave that to Martin to talk about next week. So yeah, it's so these images are created using sort of synthetic data, right? These are actually the results of applying our kind of more outward-facing algorithms that are not using our magma implementation, basically, right? So it's kind of working with floating point stuff. So we've done a little bit of testing in terms of like how robust this is to noise and so forth, and it stacks up pretty well. But we've not really, done a whole lot of robust testing at the moment. Yeah. So as I say, Martin can say more if he wishes to next week. Yeah. So what have we seen so far? Yeah. So centroids. Just to recap, centroids of a bimap are going to, first of all, tell you that what your correct field of scalars are to write your bimap over. They can also be used to detect any kind of block diagonal decomposition of your tensor and help you find it if there is one. Adjoints we've seen have an application to isomorphism testing that I've not really gone into yet, right? So I was kind of using that as motivation, and I'm not going to say a whole lot more about it, except that it does get used in isomorphism testing to shrink search spaces, right? So if you really want to, if you're confronted with tackling that brute force problem, adjoints will really help you to make that brute force problem a little bit more manageable, hopefully, right? But what we've seen today as well is that we can really leverage the structure of the adjoint algebra as an algebra. We can decompose it using this classical theory with implemented algorithms, and we can exhibit hidden symmetries in the tensor as well, right? So we can exhibit these kind of face block decompositions. And I'll just mention that the face blocks we found were kind of front to back, and the reason for that was because we were using that front to back version of the adjoints. Remember, there were 3 different choices that we could have made at the beginning, left, right, and middle, we called them. If you use those different choices, you can find blocks relative to those other faces as well. So you can sort of look for face decompositions in all 3 different faces. So that's adjoints. Tomorrow, what I'd like to do when I come back is to, well, we've seen some applications already, but I'd like to dig into the applications a little bit. I may or may not say something about the things that Martin may or may not say something about to begin with. But I'd also like to tell you a little bit about solving special cases of the tensor isomorphism problem. So there have been a lot that have been alluded to. In fact, Yuming did a really nice job of kind of explaining lots of different forms of tensor isomorphism and why they are those forms, right? Why those particular forms are actually interesting to solve problems that you might care about. So what I'll do tomorrow is to kind of lead you through one instance of tensor isomorphism that you can solve using adjoints, basically, right? And then I'll end tomorrow by talking a little bit more about p-groups. We've seen some people talk about that. Christopher's kind of done a lot of the groundwork in setting up how we make an association between p-groups and tensors. Yuming has also done a little bit of that too, kind of talking about algebra problems and like the kind of isomorphism problems that emerge from algebra isomorphism. And so that will kind of lead me naturally into saying a little bit more about the kind of tensor isomorphism problems that come up in p-groups, which we've already heard about, but also explaining how there are some subtleties there, right? You know, the kind of techniques that we can use for the general tensor isomorphism problem, you have to think a little bit more carefully about how you adapt those things to these special cases. So part of what Yuming was saying is that a lot of these problems are sort of in some sense equivalent, and that may be true, but there are some computational challenges, should we say. Some of them are a lot more easy than others computationally to kind of explain how you solve them than others are. And so I'll talk a little bit more about that tomorrow as well. So with that, I'll hand it over.